So for this unit, we're going to be starting quadratic functions. So we're going to talk today just about general quadratic functions, real life quadratic functions, and the various things that go with those quadratic functions. So it says here, what can be said of the rate of change of a linear function? Okay, the reason we know things are linear functions is because they are always constant. Now what I mean by that is that they have a slope. Okay, so they have a slope of some kind. It means it's always going up and over by the same amount every single time. The rate of change of a quadratic function is different from a linear function because they have no constant. It can rapidly grow or rapidly decline very quickly, so that's why we have no constant in this case. All right, so here are some examples, and here's a question that says, which of the following are examples of a quadratic function? A car is driven at a constant rate of speed of 55 miles per hour. The graph shows the car's distance over time of a specific time period. This is not a linear function. The reason is because it goes at a constant rate. This is a linear function here, not a quadratic, a linear. A water balloon is dropped from a third floor balcony. The graph shows the balloon's height over time period. That would be a quadratic function. When you think about it, when you're dropping a balloon, it's going to go kind of like in an arcing motion like that of some kind. A quarterback throws a football. The graph shows the football's height over time. That is a quadratic function. Sorry about that. That is a quadratic function. Think about when you have a quarterback here, he throws a football, it's going to make an arcing motion like that. The class is taking a field trip to see Les Mis. The student price is $10. The graph shows the total cost based on, this is a linear function. Okay, and the reason we know that it's a linear function, the student price is $10. So that means that for every student that goes in, it's a constant rate of $10. A diver jumps from a high dive platform. The graph shows the diver's height over the time period that he jumps. That is a quadratic function. Think about it, if you have a diver on a platform, when they jump off, it's going to create that arcing motion of some kind. Okay? One of the most common occurrences of the quadratic formula that we use, the quadratic functions in real world, is when we involve this thing called gravity. Okay? A quadratic equation is used for a free-falling body where any effects of air resistance is ignored and the coefficient for the quadratic term is constant based on the gravitational force of the Earth, which is either negative 16 feet per second or negative 4.9 meters per second. That depends on what you are talking about in terms of what is your units. Okay? This function right here, f of x equals ax squared plus bx plus c, this is the standard form of quadratic functions. Okay? A stands for gravity, B stands for the initial velocity, C stands for the initial height. So it says, suppose a volleyball player serves from the 1 meter behind the back line. If nobody touches the ball, it will land in bounds. We are given the equation h equals negative 4.9 t squared plus 3.8 t plus 1.7 gives the ball's height in meters in terms of time in seconds. We can infer several things about this situation by looking at it. From what height is the ball served? So looking at our equation, remember the height is the c value, which is that back value in the end. In this case, our height is going to be 1.7, and we know that it's in meters because it tells us that it is in meters here. Okay, so remember this c value here, this is going to be your height. Okay, what was the initial velocity of the ball? Remember, the initial velocity is the b value. So b value, which is here, is going to be velocity. So our velocity in this case is 3.28. 3.28, and it's meters per second again, because the height is in meters and the time is in seconds here. Okay. We can also gather information about a quadratic function by looking at a graph. When we're looking at a graph, there are several things that we know. Notice, okay? One is our initial height. Our initial height is always going to be our y-intercept. Okay, so our y-intercept is always our initial height. The vertex is defined by the y-coordinate gives us the maximum height. The x-coordinate of the vertex gives us the time it takes to reach the maximum height. Okay? So our vertex is in the following form. If we write it as an ordered pair of x comma y, it's going to be time comma height. Time comma height. Okay? The axis of symmetry. The axis of symmetry is the line that represents the x-coordinate of the vertex. Okay, so the equation is always x equals your x-coordinate number. So that's going to be your equation there. And then the last thing, number 4 from our graph above, the x-intercept. It gives us the time it takes the object for it to hit the ground. This is also known as the solution. We also call this the roots, the zeros, or the solutions to the graph. Typically there are 2 solutions, but in some cases there are 1, depending on what it's asking you to find. So it says the following graph represents the height over time of a water balloon being dropped from a 3rd-story window. It says from what height was the balloon being dropped. So we were looking at our y-intercept in this case. Our y-intercept is here. That is going to give us a height of 25. And you notice here it says our heights in terms of feet. So it's going to be 25 feet. And then it asks, after how many seconds does the water balloon hit the ground? So let's look at when it hits the ground. And it's about 1 1/4. So that's what we're going to say. We're going to say it's about 1.25 seconds. Okay, so now we're given an equation. So it says suppose a rocket is launched from a platform. The equation h equals a 4.9t squared plus 200t plus 25 gives the rocket's height h in meters in terms of time t in seconds. What was the initial velocity of the rocket? Remember, so velocity is our b value in our equation. So in this case, 200, and it says meters per second, so it's going to be 200 meters per second. It says from what height was the rocket launched? Remember, c is going to be your height, and c from your equation is going to be your height. Okay, so if we look back at our equation, our c is this last number back here at the end. So our c is going to be, in this case, 25, and we know it's meters because they tell us our height is in meters. It says if we measure the height in feet, how would the function change? Well, that means that all units would need to be in feet. And then it says, what would the gravity coefficient be? Okay, well, remember, there's 2 types of coefficients here for gravity. We either have negative 4.9 meters per second squared or negative 16 feet per second squared. If we were to convert from meters to feet, the feet would be our gravity that we would use. Okay, it says the following represents the height over time of a ball tossed in the air from the first story balcony. Well, from what was the height of the ball dropped? So we look here at our y-intercept here. And again, it says our height is in feet. That is at 10 feet. And then it says what was the maximum height of the ball? So we look again at the height of that ball. And we look to see where that arc is being formed, and it's right there. The height of that would be 28 feet. And it says, how long did it take the ball to reach its maximum height? So if you look from here to there, looking at our x-axis, you can see it's about 1 1/4. So that's what we're going to say. We're going to say it took it about 1.25 seconds. All right, here's a practice problem for you. If you want to pause and try it on your own before you answer, please do so. A ball is tossed in the air with an initial velocity of 12 feet per second from a height of 5.5 feet. Which of the following equations represents the ball's height in feet over time? So remember, it's a x squared plus bx plus c. A stands for gravity. So to determine there's 2 types of gravity. You got to figure out which one you're dealing with. So we're dealing with feet over seconds. So the gravity we want to use is negative 16x squared. Okay. Our B here stands for velocity. Okay, so we look for our velocity. They tell us our velocity is 12 feet per second. So this is going to be plus 12x. And then our C at the end here, that's going to stand for our height. We know our height in this case is 5.5 feet. So we're going to add 5.5 to the end. So we know our final answer is going to be C. Okay, and the last one says, consider the following from the graph that represents a projectile fired from a cannon from the roof of a high-rise building. Okay, and it says, which of the following statements is true? Okay, it says the cannon was fired from a height of 25 meters. Well, if we look at our height here, that's 50 meters, so that's not true. Okay, it says the initial velocity of the projectile was 4.9 meters per second. Okay, we know that that is not true because 4.9 meters per second is our gravity that's pulling that down, so that is not the right thing. It took the projectile approximately 2.6 seconds to reach its maximum height. So if we look here to get from our maximum height, which it does give us at the top, and our x-coordinate there is 2.55. So it did take about 2.6 seconds to reach that height. So that's true. The maximum height of the projectile was 50 feet. We know that is not true because that was the initial height of the thing. And it took the projectile approximately 6.6 seconds to hit the ground. So if we look at our ending here, it says the x-coordinate of that is 6.64. So that's about right. It did take about 6.6 seconds to hit the ground. All right, that's all we have for today's notes. If you have any questions, you can always ask me tomorrow. And good luck on your